A p-value can be understood as a continuous measure of the compatibility of numerical data with the prediction of a target hypothesis as evaluated by a specific statistical model. P-values close to 1 indicate high compatibility, while p-values close to 0 indicate low compatibility. For example, if the p-value associated with the mathematically null hypothesis of a hazard ratio equals 1 is null, p equals 0.80. According to a Cox regression model, the numerical experimental data are very compatible with the prediction of the null hypothesis as evaluated by that Cox model. Conversely, if we obtained p equals 0.001, the compatibility between the numerical data and the null hypothesis would be very low, as evaluated by that Cox model. If we change the model, we can obtain very different results. Thus, the first fundamental aspect is that such an analysis is valid to the extent that the chosen statistical model is valid. This depends on our ability to 1. Select the appropriate test for the research goal. 2. Evaluate its background assumptions. 3. Avoid experimental errors. 4. Be honest and transparent in interpreting and reporting the results. 5. Limit biases, both psychological and mechanical, by adopting proper research protocols. A confidence, or better, a compatibility interval of this form, is the set of all hypotheses that have p-values greater than alpha, as assessed by the selected statistical model. For example, if we calculate the best point estimate HR equals 3.5 and the associated 94% compatibility interval, we know that all hypotheses contained within that interval have p-values greater than 0.06. Thus, assuming the statistical model is valid, the null hypothesis HR** equals 1.0 has the same compatibility with the numerical experimental result as the markedly non-null hypothesis HR** equals 12.2. Specifically, p equals 0.06, as these are the interval limits. Furthermore, the hypothesis most consistent with the data is not the null one, but HR** equals 3.5, with a p-value equals 1, as this is the best point estimate. So, the whole scenario, usually and mistakenly considered as non-significant only because the null p-value is greater than 0.05, merely suggests high statistical uncertainty if the model is valid, and not a negligible magnitude. Indeed, the best point estimate of 3.5 is consonant with a pronounced, in most contexts, effect size. Therefore, we propose the following recommendations. R1. Check all underlying assumptions and uncertainty sources, and report the assessment procedures in a supplementary file. R2. Check the compatibility of the data with both hypotheses of low and high effect sizes. Assuming that point 1 has been appropriately performed, if the data are highly compatible with both of these types of effect sizes, e.g. a p greater than 0.20, then there is only strong statistical uncertainty, and not the absence of significance. R3. Formulate conclusions based on the type of research. Terminal conclusions, like recommendations for policymakers, must always be informed by decision analysis.